Thank you, Mr. Chairman, for the introduction, and welcome everybody to the public defense of my PhD thesis. During the last 4.5 years, many times people have asked me this inevitable question that what I was doing in my PhD. And it was kind of always very difficult for me to explain in 2-3 sentences what my PhD work was about. And by the end of my explanation, the person would think that either my PhD was too boring or it was too complicated. So, and some of my friends, and especially my father, they did not have any idea what I was doing here. And my father, at some point in time, when I told him, when I failed to explain him about my PhD, he said that he did not know if somebody can earn a living with this kind of work. But today my father is not here, but I would like to take this as an opportunity to convince my friends and my family that indeed my PhD work was very interesting, it was very meaningful, and of course it was very practical. So let's see if I succeed or not. So let me start with the outline of my presentation, which is as follows. First, I will present the scope of my PhD research. As the title of my PhD says, it is about two types of quantization: scalable single description quantization and scalable multiple description quantization. I'll talk about these two types of quantization one after the other and the associated applications and my contribution in this regard. And at the end, I'll draw the conclusions of my work. So first, the scope of my PhD research. So today, multimedia content such as image or video can be acquired using a variety of acquisition devices, some of which are shown in here. Generally, this multimedia content is acquired on a limited storage portable device. And due to its limited capacity, if we want to acquire a handsome amount of data on this device, the efficient compression of this multimedia content is very important. Also, many times we would like to transmit this captured multimedia data over some kind of a transmission network to one or more receiving devices. A very common example of this is the teleconferencing or video conferencing systems, which work by sending the captured video over the internet link. Now, compression is also very important here because the efficient the compression, the less is the consumption of your internet bandwidth. However, the main problem is that the internet consists of networks which are heterogeneous in nature. That is, the transmission bandwidth on these networks is often fluctuating and it is not constant over time. Now, to provide a good quality of teleconferencing service, the adaptation to these varying bandwidth conditions need to be done in real time. Also, in many multicast applications, the aim is to transmit the same multimedia content to a variety of end-user terminals, which may vary in terms of screen resolution, computational complexity, or memory requirements. Now, in these applications, a dedicated transmission to each type of user is not feasible. One solution that can get aligned with both the aforementioned problems of having to transmit on a fluctuating bandwidth channel and having the possibility to reconstruct on a variety of user terminals lies in the scalability of content representation. If we can represent our multimedia content in a scalable fashion, we can transmit it over a fluctuating bandwidth channel because we can adapt the transmission rate to the available or fluctuating bandwidth that we have. Moreover, the same multimedia content can now be decoded on a variety of terminals while still meeting the locally imposed hardware constraints. So in technical terms, the solution that takes care of both the compression as well as scalability issues is known as scalable compression. And in the future slides, I'll explain how this scalable compression is actually performed in practice. Now, since the acquired signal, since the camera captures this light variations using some kind of electronic sensor, the captured original signal is an analog signal like the one I have shown here. Now, an exact computer representation of this signal is very memory intensive because that would suggest saving the amplitude of this signal at all points in time. Now, people have come up with more efficient solution, and now we can sample the signal on regular intervals. But this might still not solve the problem because this sampled value is a real value which might still take infinite precision for its exact representation. Now, what we can do? We can actually discretize this sampled value, and this we can do by taking the whole range of values and then dividing it into bins, and representing all the values in a bin with one finite precision number inside that bin. This is exactly the job of the quantizer, that is to reduce the precision by representing all the values using this one finite precision number or value. Now, we can reconstruct the signal by building up this staircase-like function like I have shown the one here. And we can now decode our signal by using these line segments which connect these steps. Yeah? And you see here that the reconstructed signal is not exactly the same as the original signal, and there is some distortion also known as the quantization noise. Now we can make this quantization noise small as possible by employing a large number of bins here, but of course in that case we have to store a lot of more data on our computer also. So compression is always a compromise between the quality of reconstruction and the amount of data that you want to store or you want to transmit over the channel. Yeah. So quantization can also be used to perform compression for digital images. In computer, a digital image is represented using an array of pixels, where each pixel takes a binary code of 8 bits, and the decimal representation of this binary code is a value between 0 and 255, where 0 is the pure black color and 255 is the pure white color. Now, if we were asked to represent this picture at half of its original size, that is at a precision of 4 bits per pixel, we can do that using a quantizer. So a quantizer that has 2 raised to the power 4, that is 16 bins. An example is shown in here, where it takes the whole range of values and it divides this range into 16 bins of equal size, where each bin has 16 intensity values. And the value between 0 to 15 is reconstructed using 8, between 16 and 31 is reconstructed using 24, and so on and so forth. And if we do that, we can represent the signal at half of its original precision, half of its original data. And we see that here the quality has gone down because we have thrown away a lot of information, but now we have the original image at 50% of its original size. Now, I'm going to explain how we can incorporate scalability using a quantization system. Here I have shown a quantizer with a precision of 1 bit per pixel, and it has 2 bins, the left bin and the right bin. The left bin has the code 1, and the right bin has the code 0. And if we want to go to a higher precision, let's say 2 bits per pixel, we can take this original bin and we can divide it into 2 equal size sub-bins, where the codes of these left bin is generated by taking the code of the original bin and appending 1 to it if it is the left bin, and if it is the right bin, appending 0 to it, to the original code of the parent bin. Yeah? And the same is done exactly here also. So similarly, we can go to a precision of 3 bits per pixel, and again, we have embedded bits in the main bit, and the code is generated accordingly. Now, we can do that till we reach the precision of 8 bit per pixel. But how we are going to create the bit stream? What we are going to do is that we are going to take the first bit of all the pixels in the picture, and we are going to put it in a vector, and we call it the most significant bit plane, or the first bit plane. We take the second bit of the code for all the pixels, and we call it the second bit plane, and similarly the third bit plane till we reach the 8th bit plane, or the least significant bit plane. Now this is a scalable bit stream, because if we were asked to represent our image at a precision of 2 bits per pixel, we could have taken the first 2 bit planes and decoded the image using this second level of quantizer. And here is the decoded image, or dequantized image. And you see again the quality has gone down because we have thrown away a lot of information. Now, if we were asked to represent the image at 4 bits per pixel precision, we could have done that by taking the first 4 bit planes and reconstructing the image again. And similarly, if we have a lot more data or bandwidth available, or storage available, we could have reconstructed the signal at precision of 8 bit per pixels. Yeah, 8 bit per pixel. Now, again, it is also important to know that with the same scalable bit stream, we can adapt the transmission also, because if we have a channel that has enough bandwidth for 2 bits per pixel, we could have sent only first 2 bit planes. If it has enough bandwidth for 4 bits per pixel, we could have sent the first 4 bit planes. Yeah? So this is how scalable compression is performed. It's a very intuitive way of telling it. Actually, it is done in a more complicated way in a real system, but here I have just given you an idea. So a related aspect in networks is that the transmission is carried out using packets of fixed or variable size. Now, the network transmission often encounters packet losses due to a saturation in network capacity. Now, if we have a scalable bit stream and we don't protect it against any kind of channel losses using any kind of protection scheme, we see that the quality of the decoded multimedia content goes sharply down as a function of the packet loss rate. At the 20% packet loss rate, you see the quality is completely gone bad and it is not acceptable. Now, I would like to point out that in real-time multicast application, the classical retransmission-based solution is of not much help because it would suggest the retransmission of a large volume of data. Certainly, such a retransmission is not feasible because the network is already under saturation, which caused the packet losses in the first place. So we have to come up with some more efficient solution. And the modern solution for this problem is known as multiple description coding, or MDC. In MDC, we transmit multiple descriptions of our source over independent, unreliable channels. Here I have shown the example of two description case where two descriptions are sent over two independent channels. And if there is a loss of information on channel 2, you see that we can reconstruct the signal using the channel 1 information at some acceptable quality level. Now, if there is a problem with channel 1 and it is lost, the channel 2 information can help us reconstruct the signal again on some acceptable quality level. If both the channels are received, then since they are mutually refinable, these descriptions, they can be put together to create a fine quality reconstruction of our original image. Now, scalable MDC is an extension of fixed rate MDC that I just presented in the previous slide. And scalable MDC is an MDC system where descriptions are scalable. Scalable in the sense that they can be encoded or decoded in a scalable manner or in a progressive manner. Now, scalable multiple description keeps its advantage over scalable single description coding in two main aspects. First, no retransmission is required because an acceptable quality of multimedia content can be acquired using a reception of a subset of originally sent descriptions. Secondly, since the quality scales as a function of number of received descriptions, the quality degradation is generally quite smooth using multiple description coding, scalable multiple description coding. And this I demonstrated here. And you see that, again, at 20% packet loss rate, with the scalable multiple description coding, you have still an acceptable quality, while with the single description case, you don't have this. So let me go to the first part of my presentation, which is about scalable single description quantization. So in this first phase of my PhD, we did not limit ourselves to the traditional image or video data, but we have gone to a more advanced application domain of 3D graphics, where 3D meshes are the building block. What is a 3D mesh? A 3D mesh is basically a computer representation of real 3D objects. And these 3D mesh consist of vertices, which are points in the 3D space. And these vertices are connected with neighboring vertices using edges. And together, they make polygons. And meshes can be of different kinds. For example, they can be triangular, they can be rectangular, or made up of other kind of polygons also. Here, we'll confine our discussion to triangular meshes, for which I have shown an example here. And moreover, we'll confine our discussion to semi-regular meshes, which I will define later. Here, I'll keep myself to some more general aspects. So today, 3D meshes can be acquired using a variety of methods. For example, 3D modeling application, laser scanning, computer vision, etc. And here I have shown an example of a 3D mesh that was created by Mark Prosman using computer vision methods. This mesh has around 70,000 triangles. What Mark did is that he took the pictures of my head from different angles, and then he put them in the computer in an intelligent way to construct this 3D mesh. This mesh is not really perfect. It has certain limitations or certain imperfections. For example, here you might see that there is a small hole in my head. I mean, not in my head, in the mesh. and you see some other imperfection also. For example, that it cannot differentiate between my jacket and my skin. But that's OK, because this is a very cheap way of creating 3D meshes. We did not make use of any high-end laser scanning equipment. Still, we can get an acceptable quality. Now, today, 3D meshes have gained a lot of popularity in many areas. For example, in medicine, medical professionals use 3D meshes for modeling the human organs, and then they use these models to teach operative procedures to the students or to the patients. In virtual reality application, 3D meshes are used to create a virtual environment. And in architecture, 3D meshes are used to create the models of the building that are still to be built. And this way, they can foresee how the design will look like. And of course, the more traditional applications like computer games and motion pictures. I'm sure many of you must have seen this movie Avatar, which made a great use of these highly detailed 3D meshes.